cutting-edge proportions that foretell nimble running performance. The high levels of driving performance are made possible through the adoption of numerous new mechanisms. Detailed environmental measures and safety features have been taken while ensuring the fun of driving. Here's the dashing appearance of the new Celica, which has undergone an evolution that is well suited for a sporty vehicle of the new age. Two types of engines are available on the new Celica, depending on the destination. One is the 1ZZ-FE, and the other is the 2ZZ-GE. Both are 1.8-liter inline, four-cylinder, DOHC 16-valve and high-performance engines. Let's first take a look at the 1ZZ-FE engine. Compared to the 7A-FE engine installed on the previous Celica model, the 1ZZ-FE engine produces approximately 24% greater maximum output and approximately 12% greater maximum torque. One of the factors for this difference in performance is the adoption of the VVT-I system. The VVT-I system precisely regulates the valve timing in order to realize optimal combustion in accordance with driving conditions. For example, during full power operation, this system prevents the intake lag associated with high engine speeds, thus improving the output. During normal operation, a portion of the exhaust gases is reburned to reduce exhaust emissions. At idle, combustion is stabilized by preventing the intermixing of the exhaust gases, and the engine is allowed to idle at a lower speed to improve fuel economy. The 1ZZ-FE engine also differs from the 7A-FE engine in the piston stroke. While the bore and stroke of the 7A-FE engine are 81 and 85.5 millimeters, on the 1ZZ-FE engine, they're 79 and 91.5 millimeters, a longer stroke. This difference in the length of stroke is a deciding factor in determining the fundamental character of the engine. Let's compare these engine models with the same piston speed, but with different stroke lengths. Compared to the engine with the shorter stroke, the engine with the longer stroke has a longer crankshaft throw. With a given amount of force applied to the crankshaft, the leverage created by the longer crankshaft throw generates a greater crankshaft rotational force. This effect is the same as applying a given amount of force with a short and long wrench. The longer wrench tightens the nut with a greater torque. Generally speaking, an engine with a longer piston stroke is a torque priority type that emphasizes power in the low to medium speed range. Meanwhile, the 2ZZ-GE engine, based on the 1ZZ-FE engine, is a newly developed engine that has been created in the pursuit of sporty performance. The maximum output of the 1.8-liter 2ZZ-GE engine greatly surpasses the engines on the previous Celica models. It offers approximately 38% more output than the 2.2-liter 5S-FE engine and approximately 49% more output than the 2-liter 3S-FE engine. Let's focus on the fact that the maximum output is generated in the high speed range of 7,600 RPM. One of the reasons for the high output is that operation at such a high speed has been made possible. Here's a demonstration of that on the 2ZZ-GE engine. Compared to the 1ZZ-FE engine we saw earlier, which has the same amount of cylinder displacement, the 2ZZ-GE engine has a shorter piston stroke. Let's take another look at engine models with different stroke lengths. The engine with the shorter stroke has a shorter crankshaft throw, resulting in a higher crankshaft rotational speed with a given amount of piston speed. Thus, an engine with a short stroke is generally an output priority type that brings its ability into full play in the high output, high speed range. So the 2ZZ-GE engine has realized high speed and high output operation by adopting a shorter piston stroke. Furthermore, the 2ZZ-GE engine has adopted an evolved form of the VVTi system. It is called the VVTLi, which stands for Variable Valve Timing and Lift Intelligent. The system contributes significantly to improving output in the high-speed range. In addition to the functions offered by the conventional VVTi system, the VVTLi system features an enhanced valve lift function. In the high-speed range, the VVTLi system increases the amount of lift of the intake and exhaust valves and the length of time they remain open. Two types of cams, one for low to medium speed and the other for the high-speed range, are placed next to each other on the camshaft. In this system, the cams are used interchangeably depending on engine speed. When the engine is operating in the low to medium speed range, a proper amount of air-fuel mixture is drawn into the cylinder with the conventional amount of valve lift. As the engine speed increases, the intake air speed increases, and the resistance created by the valve prevents the cylinder from drawing in a sufficient amount of air-fuel mixture. Therefore, in the high-speed range, this system increases the amount of valve lift to minimize the intake resistance. Furthermore, the length of the time the valve remains open is increased in order to ensure the intake of a sufficient amount of air-fuel mixture. Similarly, with the exhaust valve, this system minimizes exhaust resistance to facilitate the discharge of the exhaust. Thanks to these features, the engine is able to generate higher speeds and output. Therefore, while continuing to offer the advantages of the VVTi system, the VVTLi system has been successful in providing the additional high speed and high output performance well suited to a sports-type engine. As for other features, both the 1ZZ-FE and the 2ZZ-GE engine have adopted the forward intake, rear exhaust layout. In the forward intake layout, the frontal airflow contacts the intake manifold while driving, making the intake air less susceptible to becoming heated. This results in improved intake volumetric efficiency and increased output. In the rear exhaust layout, the length of the exhaust pipe between the engine and the catalytic converter is reduced. This enables the catalytic converter to warm up more easily, thus contributing to the reduction of exhaust emissions. Furthermore, both of the engines use a cylinder block made of aluminum alloy, which significantly reduces their weight. The number of spray orifices of the injector have been increased to facilitate better atomization of the fuel, which results in the reduction of exhaust emissions, improving fuel economy, and increasing output. The engine, or heart, of the new Celica model has adopted the numerous cutting-edge technologies described thus far to realize an engine of the new age, which excels in sporty performance while maintaining its compact configuration. Bringing the engine to the limit of its capacity and maneuvering the vehicle at one's will is an ideal driving experience that is reserved for the drivers of sporty vehicles. To make this possible for the drivers who desire it, the Celica has adopted its first 6-speed manual transaxle. Compared to the 4 or 5-speed manual transaxle, the 6-speed manual transaxle enables even more precise gear changes, allowing the driver to bring the performance of the engine into full play. Some drivers normally prefer to drive in the leisurely automatic mode, but occasionally in the aggressive sporty mode. For those drivers who want everything, here's a perfect transaxle. It's Toyota's first E-Shift transaxle equipped on the 2ZZ-GE engine model. When a vehicle with the E-Shift transaxle is being driven with the shifter in the D range, it has the functions of an ordinary 4-speed automatic transaxle. However, by tilting the shift lever from the D to the M range, the driver can operate the transaxle shift switches provided on the steering wheel to upshift or downshift as if operating a manual shift transaxle. The transaxle shift switches on the front side of the steering wheel are for downshifting, and the shift switches on the back side are for upshifting. With this system, the driver can quickly shift without taking his or her hands away from the steering wheel. When the shift lever is engaged in the M range, the M mode indicator light on the combination meter is illuminated, informing the driver that the E-Shift function is ready to use. Next to the M mode indicator light, the gear position indicator illuminates the gear position that has been currently selected. During an E-Shift operation, the gears are fixed, as in the ordinary manual shift transaxle. However, if an attempt is made to stop the vehicle, the transaxle automatically downshifts to first gear. Thus, a hardcore sports enthusiast can operate it as a 6-speed manual transaxle, while others who want to drive the vehicle in a leisurely yet sporty manner can operate the vehicle in the E-Shift mode. Thus, both types of drivers can operate the vehicle to their heart's content. ABS enables stable braking even on slippery surfaces. It is a system that regulates braking by detecting if a wheel is about to become locked. This system has been further developed into one that properly regulates the brake force distribution before the wheels become locked, thus making it possible to provide excellent braking performance. Adopted on the new Celica model, it's ABS with EBD, which stands for Electronic Brake Force Distribution. In ABS with EBD, the brake force distribution that was performed mechanically in the past is now controlled electrically. As a result, proper brake force distribution, in accordance with the vehicle's driving conditions, has been achieved. In addition to the front-rear wheel brake force distribution, this system also affects right-left wheel control. Let's see how this system operates. If the brakes are applied when the vehicle is being driven in a straight line, the shifting of the load causes the load applied to the rear wheels to decrease. During cornering, the load applied to the inner wheels is also decreased. In this case, if the same amount of braking force is applied to all 4 wheels, the wheels with the decreased load become susceptible to locking. ABS with EBD detects these conditions through the wheel speed sensors and uses the brake actuator to properly control the brake force distribution to the 4 wheels to enhance braking performance. If the wheels are about to become locked thereafter, the conventional ABS function is activated. ABS with EBD detects the conditions of the wheels in this manner in order to properly distribute the braking force. Therefore, even if there are changes in the loading conditions or the extent of braking, proper braking force is maintained at the four wheels, thus providing excellent braking performance. Now, let's observe how the amount of valve lift is changed by the VVTLI system. Two types of cams, one for low to medium speed and the other for the high speed range, are placed next to each other on the camshaft of the VVTLI system. The high-speed cam is made a size larger than the low and medium-speed cam in order to create a greater amount of valve lift and to prolong the length of time the valve remains open. At low to medium engine speeds, the movement of the low and medium-speed cam is transmitted via the rocker arm needle rollers to push the rocker arm down in order to push the two valves open. Simultaneously, the high-speed cam also pushes the rocker arm pad in the rocker arm. However, as the illustration shows, the rocker arm pad moves freely in the rocker arm without transmitting the movement of the high-speed cam to the valves. Then, when the water temperature is 60 degrees Celsius or higher and the engine reaches a speed of 6,000 RPM or higher, hydraulic pressure causes the rocker arm pin in the rocker arm to slide under the rocker arm pad, as you can see. Thus, the movement of the rocker arm pad becomes fixed. As a result, the movement of the rocker arm pad is also transmitted to the rocker arm, enabling the high-speed cam to depress the rocker arm even further than the low and medium-speed cam. This simultaneously increases the amount of valve lift and the length of time the valves remain open. Now, let's take a look at the hydraulic pressure control that affects this change to the high-speed cam. The OCV, which stands for Oil Control Valve mounted on the cylinder head, regulates the hydraulic pressure directed inside the rocker arm. When the engine is operating at low to medium speeds, the OCV remains off and the hydraulic pressure is directed to the drain side without being sent to the rocker arm. When the water temperature is 60 degrees Celsius or higher and the engine reaches a speed of 6,000 RPM or higher, the OCV is turned on, thus shutting off the hydraulic pressure directed to the drain side. Therefore, the hydraulic pressure travels via the hydraulic passage in the rocker's shaft to the rocker arm, enabling the high-speed cam to operate. Now, let's look at the disassembly and assembly precautions associated with the VVTLI system. Use the new SST for removing the valves. Using the SST, compress the valve spring and remove the two valve keepers. Remove the spring retainer and the valve spring and take out the valve. Pay attention to the position of the hydraulic passage hole when installing the rocker shaft. Face the slit of the rocker shaft up, Align the shaft end with the cylinder head end, locate it with the bolt, and secure it in place. The coolant replenishment method has been changed. Place the reserve tank at a higher position than the engine. Detach the hose of the reserve tank from the hose clamps, lift the reserve tank, and fix it by hooking it onto the hood lock. Remove the reserve tank cap and the air bleeder plug. Pour about 3.7 liters of coolant to bring the coolant level to the full mark on the reserve tank. With the cap and the plug removed, start the engine. Warm up the engine completely. At this time, switch off the air conditioner to prevent the coolant from overflowing. Keep the engine running at idle and pour in an additional half a liter. Securely tighten the plug and the cap. Race the engine repeatedly and operate the engine for 15 minutes or longer. Allow the engine to cool down completely. Then, make sure the coolant level is between the low and full marks on the reserve tank. To understand the operation of ABS with EBD, let's see an example of how this system functions when the driver applies the brakes while the vehicle is being driven in a straight line. When the brakes are applied, the wheels begin to decelerate. A wheel speed sensor is provided at each wheel to detect the slippage of the wheel. If the system detects that the rear wheels are susceptible to locking first, it affects front rear wheel electronic brake force distribution control, or EBD. Under EBD control, the brake actuator's pressure holding valve for the rear is turned on. This stops the increase in pressure to the rear wheel brakes and holds the brake pressure. From this state, if the driver depresses the brake pedal even further, the brake pressure increases only in the front wheel brakes. As a result, the slipping conditions of the rear wheels recover relatively, and the pressure holding valve for the rear is turned off to resume the increase in brake pressure to the rear wheels. As the driver continues to apply the brakes, this operation is repeated in order to properly distribute the brake pressure between the front and rear wheels. If the driver depresses the brake pedal even further, and the wheels are about to become locked, the conventional ABS control takes over. The EBD utilizes a part of the ABS functions in this manner. Therefore, if the EBD malfunctions, the ABS also invariably malfunctions. In this case, the ABS warning light and the brake warning light illuminate simultaneously to alert the driver. However, if the ABS malfunctions, it is not necessarily accompanied by the malfunction of the EBD. In this case, only the ABS warning light illuminates.